Okay, so for today's class, we are going to be looking at exponential models. One of the goals of this one is to identify the horizontal asymptote of an exponential model. So one of our goals from today is to identify the horizontal asymptote. So I thought I'd start with one of the questions from the exam we just took, where we looked at finding horizontal and vertical asymptotes. And I'll show you some calculator skills. So if you follow along on your calculator, I want to kick off with a little bit of a review of finding horizontal and vertical asymptotes. So we had this question. Sorry, Leah, can you not talk and disturb people if you're coming in late? Take out your notebooks, take out your calculator. Right, so take this function and enter it into your calculator. Enter this function into the calculator. So you can follow me along as well. I would start by pressing the on button. Press 1 for a nice new fresh document, always add a calculator page. And then press Control, add page, and add a graph. Let's type in our function here. That's as zoomed in as I can get. If you need to see better, take your stuff and go sit right in front of the screen. Yeah, but your angle because of your angle to the screen, it increases it. So why don't you come and sit next to Zaki? Okay, so type your function in, press Control, divide. We get our quotient. We want 2x minus 3 over x minus 4. Our graph looks like this. Now, our first task is to find the vertical asymptote. We want to find the vertical asymptote. Now, the vertical asymptote for this type of a function is the value that will make the denominator equal to 0. So there's a couple of techniques we can do. We can see that what value do we put in that will make that equal to 0? 4. We can see it very clearly. If it's a more complex function, you could use nsolve. So we could use algebra, nsolve, and this is a bit simple. X minus 4, we take the denominator, set it equal to 0, and solve for x, and we get our answer. X is equal to 4. If we suspect it is 4 by looking at it, if you try and trace a graph at a value that's not defined, so if I type in x equal to 4, press enter, I get this vertical line. It draws the asymptote. Notice here it says when x equals 4, the function is not defined. So it draws the vertical asymptote for us at that particular point. So we have the vertical asymptote at x equal to 4. Bon. We can just see it. So Bon is now pointing out the really obvious is when it gives a well-defined function, it defines the domain. And here when it defines the domain, it says x is not equal to 4. Now, some people got this question wrong. I marked it right this time, but in future I'll mark it wrong because I think Seyun, I think it was you that was doing this, as they said that the vertical asymptote is x is not equal to 4. Now, that is not the asymptote. The asymptote is x is equal to 4. It is not defined when x is not equal to 4. But the asymptote is the equation x equals 4. So it has to be quite precise on that one. Horizontal asymptote, we can see it's around about here. But it is harder to find. Let me show you a simple technique. So go onto the calculator screen, pull up the variables. There's F1. That's the function we entered it in. So put in larger and larger values for x. So if I put in 100 and I press, let me do Control Enter when if I get a fraction, 2.05. I'm just going to press document 7.2 and change my float into full float. And then I'm going to press Control Enter again. And I see 2.05, blah, 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 blah. To get the F1, I press variables here, above the 9. Above the 9. Now I'm going to put in 1,000. And I'm going to press Control Enter. Notice it's 2.0005. It's got a little bit smaller here. I'm going to repeat that for an even bigger value. I'm going to put in a really big value now. And I'm going to remember to press Control Enter. Notice, if we were to round this to 3 significant figures, what number would we get? 2. What you see in these calculations is as I put in bigger and bigger values for x, the function is getting closer and closer to 2. It's displaying that asymptotic behavior. So the asymptote of this function, I can add it, is y is equal to 2. And what's happening is as I'm putting in bigger values, it's getting closer and closer to 2 without ever being 2. And that is the idea of an asymptote. So this is how we can find the equation of an asymptote. It will never touch 2. But if you put in such a big value, the calculator can't handle it and it will say 2. But it's actually not. It's just off of 2. Mathematically, it can't handle really big numbers. Okay. We press tab. And we can get f of x equals, and we can put y equals 2. Okay. So in what interval is the function increasing? Well, we can see that this function is always decreasing. It's never going up. Harmon, are we focused? Next, we need to find when is the function equal to 0. When is the function equal to 0? We can see it graphically. It's here. It's this point here. If we look at the graph, it only crosses y equal to 0 once. That's there on the x-axis, and that is the zeros. So we can analyze graph, find the zeros. We want the zeros of this graph. It's happening there at 1.5. Graphically is the best approach to doing this. If there's multiple zeros, you'll see it. If there's multiple zeros, you will see it. Let me show you, I'll take your question in a second. Let me show you another technique for finding zeros. So another technique for finding zeros, and we really need to get good at using nsolve. So we could take the function f1 of x and say we want, when is this equal to 0? Solve for x. It will give you an answer. Now, one of the problems with nsolve is it only give you the answer closest to 0. If there's multiple, you might miss it. But you can tell nsolve to keep looking for bigger values. So if I tell it to look for values bigger than 1.51, it'll say no solution found. That's because there is no more. But if there was another, it would show us. We would also need to check the negative direction. So we might want to go from negative 1,000 up to 0 and see if there's anything in this interval. It's going to say no solution. So these last two, firstly, I was looking in this section here, and then I was looking in this section here, and there is no solutions there. But graphically is the best way of finding the zeros because you see if it crosses more than once, but nsolve is also a very useful technique for finding the zeros this way. Sam? Yeah, so part C is when is the function increasing? It's not increasing. All it does is go down. It goes down and it goes down. So the answer for part C is it's never. So what if it's increasing? What's the interval? It's not increasing. So if it was increasing, depending on the shape of the graph, the interval will vary depending on the shape of the graph. But for this graph, it's not increasing. But how are we going to inequalities. So you would have to look at the graph. Let's do a graph that does increase then and show you how it might look. So if I added a different graph, let's say I have the graph 4x minus x squared. This graph is increasing and decreasing, so it would be depending on the shape. So obviously this graph is increasing from negative infinity until the turning point. And I would have to analyze the graph for this one, find the maximum. This graph is increasing from negative infinity up to 2. So from negative infinity to 2 exclusive. All right, let me move back here again. So our last one Our last one is find any points of intersection with this line. Now, the technique I was expecting you to do that day was to rearrange this equation to make y the subject. Let me show you a new technique you can use for this one. So you can actually enter in functions in that form on the TI Inspire. We can press Menu, Graph, enter a relation. So if we enter a relation now, it'll allow us to type it in as we see it. Minus x plus 2y plus 9 equals 0. It would let us enter it in, and then we can find the intersections. So we can find the intersection between this graph and this graph, between here and here. So we can, there is only so many things I can tell you during the different lessons. At that, as I said in my second ago, I expected you to rearrange the equation to make it y equals, which was a skill we had worked with and I wanted to test. Analyze graph, find the, analyze graph, find the intersection. We have to select that graph and that relation, and there. We can see 4, 3, and 14 as our solutions. All right, let me move on. So you're going to need your computer open on this one. I would like you to investigate exponential functions. Go to the Google Classroom. Go to the Google Classroom. Click on this link. You have the link in the Google Classroom, so it will open up to GeoGebra looking like this. And then we can move these around. All right, so we're investigating a little bit what A, K, and C do to the shape of this graph. I'm going to look to begin with A. Notice as I make A bigger how the graph changes. What do we notice? We notice it changes. And then if I make it smaller, it does something weird here at this point. Okay, so I can see that the graph either goes down or it goes up. So now I want to investigate the values that make it go down and which values make it go up. So if I notice anything from 0 up to 1 will make it go down. Anything from 0 up to 1 will make it go down. So let me express that in terms of math. So the function is decreasing. The function is decreasing. I don't know where that came. The function is decreasing. And we need to express that in math. It's an interval. 0, and that was, it was A, up to 1. So I answer it with an interval. Let me go back to the graph and see what's happening here now on the graph. So if I make it bigger than 1, it increases. But also notice that as we make it go bigger, it increases faster and faster. So it will increase faster and faster the bigger the value of A. And it will decrease faster and faster the smaller the value of A. So at 0 is when it's just off of 0, 0.1 in this case, is when it's decreasing fastest. And as I get closer to 1, it's decreasing slower. And here it's decreasing slow and then fast. So now I've investigated completely what the value of A does. So it is increasing when A is greater than 1. Notice I'm not using greater than or equal to, because at 1 it was a flat line. It's not allowed to be equal to 1. So A can't equal to 1 because when A is equal to 1, we don't have an exponential function. When A is equal to 1, we have a linear function. That's a straight line. So A can't equal 1. A has to be bigger than 0 and cannot equal 1 for this function. So next up, I want you to investigate the horizontal asymptote. How can we determine the horizontal asymptote? Then I want you to investigate how can we calculate, according to A, C, and K, what the y-intercept is going to be. Do those two investigations now for yourself. Right, so first up we want to see the horizontal asymptote. That's that red line here. So we can see this dotted red line which shows the horizontal asymptote, and we want to see what changes it. If I wiggle A, makes no effect. If I wiggle K, it makes no effect. But if I move C, it changes it. So I can see that C, the horizontal asymptote, is affected only by C. So when C equals 2, the horizontal asymptote is y equals 2. When C equals 4, the horizontal asymptote is y equals 4. When C is negative 3, the horizontal asymptote is y equals negative 3. So it's very clear that we can see the horizontal asymptote is the equation y equals c. So whatever c is will give us the horizontal asymptote for this function. Is there an easy way to calculate the y-intercept? So looking for the y-intercept now. So the y-intercept here is minus 1. What affects it? Let me bring this back up. So I'll start by wiggling A. The y-intercept is at 2, and if I wiggle A, it doesn't change the y-intercept. This one has no effect on the y-intercept constant. If I change K, oh, the y-intercept's changing. So I've got 4 when I have K equal to 4. I've got 3 when I have K equal to 3. But take care, because C also affects it. It's a combination of these two. So when I have C equal to 1 and K equal to 3, it's at 4. How do the numbers 3 and 1 relate to 4?
A plus C equals 1.
Adding them. So that's our conjecture. We make the conjecture that maybe C plus K is the horizontal. So we test the conjecture. If I change this to 4, it should go up by 1. If I change this to minus 1, it should go down by 2. And it does. So just testing here, I've got minus 2 plus 4 should be 2. Yes, it is. Let me test a few more values. So minus 1, minus 2, it's minus 3. So we can see at this particular point that the y-intercept is going to be at y equals k plus c. Or, let me put it as a coordinate point, it's going to be 0, comma, k plus c. This will be the coordinate of the y-intercept. Lastly, which type of exponential equation causes growth, which causes decay? So on this one, notice what k does is when k is when k is negative, it gives us a reflection. So this one is a stretch and reflection. So I'm going to make this one positive, I'm going to make this one 0. Because growth and decay, we don't have, this is a decreasing graph. It's not a decay graph, because no physical concepts have negative values throughout. So we don't tend to consider this one to be growth and decay. Growth and decay is when k is positive. So it's the a value. So when a is greater than 0, we get growth. When a is between 0 and 1, we get decay. So these are the values that are the same as decreasing and increasing. Growth and decay is a positive concept. Let me just give an example here. So this would be if you've got the population is decreasing, it might look like this. So if the population is decaying or radioactive decay, this one looks like this. If you have a population growing, bacterial culture, it might look like this. It's growing. So the only graphs that sort of have values in the negative would be something to do with maybe temperature. There's not many concepts. So if you imagine, if you're counting people, it's positive. If you're counting bacteria, it's positive. So a lot of concepts that we model, they tend to be only positive values, because that makes sense. There's not much we model with negative values. Maybe money or temperature. But temperature doesn't decay or grow. It increases and decreases. So it wouldn't be a good model. So typically, growth and decay is positive concepts. All right, that's the end of our investigation. Exponential functions can be used to model real-life functions. So this is typically where there's a constant percentage change. So exponential function is when we have a constant percentage change. And then we saw these results here. All right, pair discussion. For each of the following functions, find the equation of the asymptote. Use your calculator now for this one. Find the equation of the horizontal asymptote. Find where it cuts the y-axis and state whether it's increasing or decreasing. You can either use your calculator or you can just look at the values and use the ideas that we've just done for these two. Discuss in your pairs. 2 minutes. Let's have a look here now. So what we want to do for each one of those is use the information that we just found. So the equation of a horizontal asymptote, that's y is equal to c. A general form was y is equal to k times a to the x plus c. So when we have a function in this form, we can say the horizontal asymptote is y equals c. The coordinates it cuts the y-axis is going to be 0, comma, a plus c. Sorry, not a, k plus c. And increasing and decreasing. Increasing is a is greater than 1, and decreasing is when a is between 0 and 1. So let's do this now. So for a, we have the function f of x is equal to 3 to the x plus 2. The value of k here is going to be 1, which is why we don't see it. A is equal to 3, c is equal to 2. So to answer our questions, I is going to be y equals 2. I is going to be 0, comma, 1 plus 2. So 3. And I is going to be, is it increasing or decreasing? It's going to be decreasing. It's going to be decreasing because a is between 0 and 1. I can come and have a, oh sorry, I'm getting confused. You're right. You're right. I'm reading this one. I'm reading this one. Sorry, a was equal to 3 here. I'm reading the wrong one. So this one is increasing because a equals 3, which is greater than 1. Thanks. All right, so the next one is f of x equals 5 times 0.2 to the x minus 3. K equals 5, a equals 0.2, and c equals negative 3. So in our first question, what is the equation of the horizontal asymptote? That's going to be y equals minus 3. The y-intercept is going to be at 0, comma, and we need 5 minus 3, so 2. And is it increasing or decreasing? Yeah, this is the decreasing one. This one is decreasing. Because a is between 0 and 1. A is equal to 0.2 on this one. Okay. We have an example question here to do. Have a go at this question. Try and figure it out for yourself for 2 minutes, and then I'll run through it. So, we have the problem, Saul buys a tractor, and the tractor reduces by 0.8 each year. Why can I not do 51,000 minus 4 times 8% of 51,000? Sorry, 8% of 51,000. Why can I not do this?
each year it's going down, so the 8% is going to be of the new value, not of the 4,000.
Exactly. So what we're doing here is so this calculation, let me just break it down for you. This bit is calculating 8% of 51,000. And then this is making 4 lots of it, and we're taking it away. Now 4 lots of it assumes that the value doesn't go down. And what Camille says is that after the first year, it's no longer worth 51,000, it's worth less. So we need to use a compound decay model for this problem. So what we want to do is we want to multiply 51,000 and we want to reduce this by 8%. What do we multiply it by to reduce it by 8%?
1 minus 0.
Yeah.
0.
We multiply by, I'm going to do it this way, 1 minus 8%. So let me do it all in percent. We want 100% minus 8%. We want 100% minus 8%. Now that is 51,000 multiplied by 1 minus 0.08. 100% is 1, 8% is 0.08. So that is 51,000 multiplied by 0.92. So we're going to multiply by 0.92. Now, that's going to reduce it 1 time by 8%. How do I make it reduce it more than 1 time by 8%?
Like, you put 4, like tiny 4, I forgot what's it called, exponents?
You make the exponent 4. Exactly. So I'm going to start off by making it x, just to make a general model. And we'll take the cost in terms of x after x years would be given by this general model. So then what we want to do is find c of 4, which will be 51,000 times 0.92 to the power of 4. If we pop this into our calculator, I'll just pull my calculator up. We want 51,000 multiplied by 0.92 to the power of 4. When you're doing currency, it should always be 2 decimal places. So typically we answer everything in 3 significant figures or exact, but currency, 2 decimal places is the standard. So on your calculator, press document 7.2 and put it into fixed 2. This is 2 decimal places. So the answer here would be 536.04. So 36,000. What's our unit? What's our currency? Dollars. $36,500 approximately. So B. B, we need to find out how many years until the tractor is worth half its original amount. So half the original amount would be 51,000, it would be a half times 51,000. This has to equal 51,000 times 0.92 to the x. Now, those 51,000s cancel each other, and this simplifies down. We want basically a half to be equal to this. So we can find this on our calculator now. Oh, sorry, to the x. So we want to solve this on our calculator. I think the best technique for us at this point is to use NSolve for that one. So menu, algebra, NSolve. We want a half, 0.5, to equal 0.92 to the power of x, and solve for x. This is when we get x is equal to 8.31 years. Now, reread the question. Find the number of years until the tractor is worth half its original value. So, with this, question. It says the price of the tractor he uses 8% each year. It's not continuously going down, it's going down in a compound model. So after 8 years, would it be worth 51,000? Would it be worth half of 51,000 or not? So half of 51,000 is 25,500. So after 8 years, do we want 8 years or 9 years?
9.
So we want a value which is bigger than 831, and in this case I think we want x is equal to 9 years. Then it is more than halved. Then it is more than halved. All right.
Can you explain the 0.92? What is that?
The 0.92, this is an 8% decrease. So the 0.92, you can see in my calculations here at the beginning. So we want 100% minus 8%. So we want to reduce the whole, which is 100%, by 8%, to go down by 8% each year. So 100% minus 8%. Convert the percentages into decimals, and we get 1 minus 0.8. This is where the 0.92 comes from.
And x is the number of years.
And x is the number of years. Okay, so that's it for the lecture today. I think we're going to do a Kahoot activity now. So get your calculators out. Your calculators, get your devices out.